In this episode, we will make meteors fall from the sky. When they collide with the jet will explode and the game will end. A screen will then appear showing the high score and a play again button. To accomplish this, we first need to load the meteor image from the application resources. Similar to how we previously loaded the jet image using the function image resource in image bitmap. You will find the image named rock_small_copy in the project files. Next, we will define some essential constants. Rock scale. To adjust the meteor size, set to 0.35 f. Rock speed. To control its downward movement velocity, set to 5 f. Rock radius. To calculate the collision area to be used later for collision detection between the meteor and the jet, calculated as the image width multiplied by half the meteor scale.
We don't want to draw just one meteor, but multiple meteors continuously falling from the top of the screen. To achieve this efficiently, we will use a recycling technique. We start with a limited number of meteors, and when any meteor reaches the bottom of the screen, we reuse it by repositioning it at the top with a random horizontal location, allowing it to continue falling as if it were a new meteor. To accomplish this, we will define a variable named rocks its type list offset. This variable will create a list containing 5 elements, where each element represents a meteor's position using offset x, y. We mentioned this in previous episodes. Offset is an object containing the coordinates of object on the screen. X is horizontal position, left and right, and y is vertical position, up and down. And here random.next float multiplication screen width px. This generates a random number between 0 and the screen width to place the meteor at a random horizontal position. And random.next float multiplication screen height px division 2. This generates a random number between 0 and half the screen height, so that the meteors appear scattered in the upper portion of the screen and don't all start from the same point.
Now, to draw the meteors on the screen using the canvas, we will adapt the jet drawing code by adding a for loop. Copy the code that draw the jet, and add for loop inside the draw into canvas part. That iterates through the elements of the rocks list. And by using the scale variable rock scale and modifying the position of each element in the list, we obtain a loop that produces 5 meteors at different locations. It's important to make sure you've modified all the necessary values when copying a piece of code to avoid mistakes. I often forget to modify a value and an error occurs. Now that we have created a list of meteors, we need to continuously move them downward to simulate falling. We use launched effect to safely initiate a loop within Compose. You may recall this function from the first video of the game. Since we want the rocks to keep moving as long as the game is running, we add a while loop with the condition true to make it run indefinitely. The delay 16L line means we wait 16 milliseconds between each update, which ensures smooth rock movement. Similar to games running at 60 frames per second. We then create a temporary list to store the new positions of the meteors.
But how can we move multiple rocks using the same code?
The solution is to use a loop that processes each rock individually and updates its position separately, allowing all of them to descend over time. Inside the loop, we define a variable that stores the new position of each specific meteor by taking its previous position and adding the meteor speed to it. We then check whether the new meteor position is within the screen bounds. If yes, we add it to the temporary meteor list. And recall that it is a list composed of meteor positions. This loop adds only the meteors whose positions are within the screen boundaries. Therefore, after this loop, we will need another loop that adds new meteors to replace those deleted from the temporary list. We use a while loop with the termination condition being when the number of elements returns to 5 in the temporary list. And again, we use random to place the meteor at a random position at the top of the screen, just as we did when initially defining the original list. Thus, the temporary list becomes complete, and we can update the original list with it. The slight difference between the two lists is what creates the movement effect.
After updating the values of all elements in the temporary list, we assign them to the original list. This shifts the positions of all meteors on the screen by a small increment. Since we are using remember and mutable state of, any change in the position values triggers an update of the graphical elements on the screen. As a result, we achieve smooth movement of the meteors across the display.
The big question is, how do we program the meteors to explode when they collide with the jet? Because currently nothing happens. They just pass through each other. To create a collision, all we need is to define a collision area. What is this area? It is essentially an invisible rectangle drawn around the jet, representing the boundaries that, if a meteor enters, will trigger the jet's explosion. To draw this rectangle, we use the rect function, which accepts the rectangle's location and its dimensions, width and height. We should make the collision area slightly smaller than the jet's visual size to allow some leniency for minor contacts, and to make the game more exciting from a gameplay perspective. In this case, the area is 20% smaller than the jet's visual area. First, let us define the collision area for the jet. As mentioned, we use the rect function, which takes the rectangle's position and its size. Here the position corresponds to the jet's location, and the rectangle's size corresponds accordingly. Remember that we scale the image before drawing it, so the actual size is obtained by multiplying the image dimensions by the scale value, and then by 0.8 to create a collision rectangle that is 20% smaller. This operation must be executed in both the horizontal and vertical dimensions.
Now, inside the loop that updates the meteor's positions, we define a collision area for each meteor. We simply repeat what we did before, changing the position to the meteor's position and adjusting the size likewise. For each meteor we test whether the two rectangles overlap using the overlaps function. If an overlap occurs, that means we should show the explosion image. To do that, we store the jet's current position in a variable to represent the collision location. You can expect this variable type.
We also define a Boolean variable to control whether the explosion image is shown on screen, named showExplosion. Let's load the explosion image from the project resources. You can find it under the name small_explosion_image. When a collision happens, we set showExplosion value to true and proceed to draw the explosion on screen using the same drawing code we used for the jet. But with the explosion image and the appropriate position. The explosion is drawn only if showExplosion is true, and the collision position variable is not null. Then we adjust the display location and the image is needed. Run the code like this and boom! When a collision occurs, the explosion appears, and it appears exactly where the jet was. Cool!
The time has come to implement the end of the game by stopping the counter at the moment of the jet explosion and also stopping the falling meteors. First, at the beginning of the program, we define a Boolean variable called is_game_over. Based on its value, certain modifications will be applied. Naturally, its initial value will be false at the start of the game. The moment this value changes to true is when a collision occurs, that is, when two rectangles intersect. The first element affected by this variable is the counter, which must stop increasing. Therefore, we add a condition that the variable's value must be false in order for the counter to update. Now, to stop the meteors from falling, we apply the same condition inside the loop responsible for rendering the meteors. Let us now take a look at the game to observe what happens. Indeed, the meteors stop descending. Of course, the jet is still moving, but the important part is that the timer freezes at the moment of collision, which represents the player's score. Our next task is to save this result.
We already have a variable to store the current score. Next, we add another variable dedicated to storing and displaying the high score. As is commonly known, a high score should always be persistently stored in the game. To enable this functionality, we need to add a library dependency in Gradle. Simply add the following line to the module file and synchronize the project to download it. Now, let us add a new Kotlin file to the project named Score Manager. No need to worry, we will explain everything step by step. We start by defining an object and naming it Score Manager. In Kotlin, an object ensures that only a single instance of the class exists during runtime. It is typically used when we want a centralized place to access shared functionalities such as saving and retrieving scores. Preferences Data Store. This is a helper function that creates a data store for saving application settings and preferences. It generates a dedicated storage file for app preferences. All you need to provide is a unique name for this file. The function then returns an easy way to access and manage this storage.
Next, we define a constant key used to access the high score value inside preferences. High_score_key is the identifier we will use to read or write an integer value. The save high score function is declared as suspend because it performs asynchronous data operations. Its role, to save the given score, but only if it is higher than the currently stored value. The keyword suspend ensures that saving the high score runs in the background without pausing or slowing down the game's movement. Call this function inside launched effect in Compose or within lifecycle scope.launch in an activity to avoid blocking the user interface. And here we read the current value of high_score from prefs. If it does not exist because it's null, we take the default value 0 using the question mark.
The getHighScore function returns the stored high score as an int. It is also declared as suspend because it performs a read operation from the data store. Context.dataStore.data represents the storage box that contains all application preferences. .first function means we take the latest saved value currently available in memory. Then, we return the last recorded high score at the point where this function is called. All preferences related to the high score are managed inside Score Manager. That is why we use it within the game logic. When a collision happens, we call the function saveHighScore, passing in the context and the current score. The function automatically checks whether the new score is higher than the one already stored. After that, we store the updated high score inside its dedicated variable for later use.
Now we need a screen to display the high score. To achieve this, let us define a variable that controls its visibility. similar to the variable show_explosion. We will define a new variable named show_replay_panel, initialized with the value false. Next, let's write the code for the screen controlled by this variable. Below the code responsible for drawing the jet, we first check if the value of show_replay_panel is true. If so, the panel will appear. First, we define a box and make it fill the entire screen. Inside it, we add a background image to represent the crashed jet by using the resource jet_crash. We also attach a content description A and make the image fill the screen. On top of this background, we add the content in a vertical column that also covers the full screen. To center the content, we set the vertical arrangement to center and the horizontal alignment to center horizontally. The first item we want to display is an image with the text "Game Over." For this, we can copy the previous image code, adjust the name and content description, and set the size to 180.dp.
Next, we add a score box using a text composable to show the player's result. We apply padding of 8.dp. Set the font size to 24.sp. Text color to black. And the background color to white. We then duplicate the same code to display the high score. Changing the label accordingly, and using blue color. Finally, we add an image label "Play Again," taken from the project resources. We make it slightly smaller and wrap it with a clickable. When clicked, the following should happen. Reset the player's score to 0. Reset the jet's position to the starting point. Hide the explosion image by setting show_explosion to false. Set is_game_over to false. And hide the replay panel by changing show_replay_panel back to false. To trigger this panel correctly, its value should become true only after confirming a collision. With a short delay of around 400 milliseconds, the time needed to display the explosion effect. At this point, we also add a break statement to stop the loop execution. Now, let us run the code.
When the game ends, the panel successfully appears. At first, we may notice a small mistake: the blue color applied in the wrong place. Such issues are common, and patience is always needed. After fixing the placement, by moving the blue to the background. And run the code again. It looks much better.
With this, we have explained the main features of our game. Of course, there are many possible improvements, but for now, we have covered the fundamentals.
Through this project, we have broken several barriers by working with Canvas and Jetpack Compose, and we started using Kotlin in an engaging way. I encourage you not to stop here, keep improving and expanding the game further.
The full project is available on GitHub, link in the description, where you can download it easily. And one final note, this channel has just started. If you find the content helpful, you can support it by pressing the like button and subscribing.